So part E, we're at the equivalence point. This is how I know we're at the equivalence point. The molarities of both the acid and the base are 0.249. You have 20 milliliters of this, so you would need 20 milliliters of that, and that's what we have. It is not important that you recognize you're at the equivalence point here, okay? But I do see that. Now, if I recognize it, I prepare myself, because being at the equivalence point is a lengthy process, one that we expect you to be able to do. It starts out just like all of our other examples, okay? Everything that we've done so far has started with an ICF table. And I'm actually going to grab a paper towel, because I want to scrunch this up just a little bit, because I've got to save room for all of the extra work, okay? ICF. Now, I've got the value of 0.00498 that I've been using here, because that has not been changing from problem to problem. If I didn't realize I was at the equivalence point, how would I know I was at the equivalence point? Well, I go blindly doing the next step, which is to get the moles of OH minus, right? To get the moles of OH minus, I take the molarity of 0.2. Oh, there's a typo there. Has that typo been there all along? Hang on a second. Yeah, it hasn't. Good. That's supposed to be a 9. That was not supposed to change at any point along this problem right there, so I will fix it right there. 2.9 is my sodium hydroxide solution. Okay, 0.249 moles per liter times the 20 milliliters. Okay, so that would give me the liters, and that would give me this value, 0.00498, because it's the exact same numbers that gave me that value before. So I'll put moles there. This is moles of hydroxide. Remember, in this ICF table, it's a limiting reactant problem, and we compare using moles. Again, nothing, and the water there for that number. Now, maybe at this point I recognize it's the equivalence point, because the definition is when you have equal mole amounts of the acid and the base in your titration, okay? We will subtract the smaller of the two. Well, they're both the same number, so I will subtract 0.00498 and add 0.00498. This consumes the acid. This consumes the strong base. This produces all of the conjugate base of that weak acid. So this is, and I want to remind myself, moles. So when I examine the F line, which is what I always do at this point, I say, what is in there? Well, I don't have any weak acid, I don't have any strong base, but I have a weak base in this solution. This weak base is sitting in water and will do what weak bases do. This is always where you are at the equivalence point. You've consumed these and you have produced a weak, okay? Weak acid or base, you have to decide, but this right here is the conjugate base of this acid. Well, what do bases do when they're in water? Well, bases undergo equilibrium with water to reestablish a certain amount of its conjugate acid, and if it's accepting a proton from the hydrogen, we are going to make the HA, and the water becomes OH minus. So this is aqueous, aqueous, well, that's water, which is a liquid, and aqueous. So there is the reaction that's taking place next. Now, this reaction is always taking place. It's just that we can skip it when we're a buffer. The Henderson-Hasselbalch equation basically does all the steps for you for this with some good assumptions that don't get to apply always, okay? And the Henderson-Hasselbalch equation cannot be used unless you are a buffer. So we have an equilibrium, so we don't have an ICF table, but we're back to our ICE table. In our ICF table, we plugged everything in moles because this is a way of doing a limiting reactant problem. In the ICE table, we want to use molarity, okay? We want to come up with the molarities to plug into the table. So now what do I have? I have how many moles of A minus I have, right? But I want to know the molarity of A minus, which is the moles of A minus, check, got that, over the liters of solution. Well, how many liters of solution do I have? Well, I have 20 milliliters of the acid and 20 milliliters of the base. So to get the molarity of this A minus, I'm going to take the moles, which comes out of this table, and I'm going to divide by the volume, which is 20 milliliters, which is this many liters, plus 20 milliliters, which is this many liters, and that will give me the molarity of this anion. The value for this is 0.12. I'm carrying an extra sig fig along for the ride, 1245. All right, so where do we want to put that? That is the molarity of the acid, so it goes right here. This is how much we would have if it all stayed in this form. But we know as a weak acid, it doesn't stay in this form. It reestablishes an equilibrium with its conjugate. Before this takes place, we didn't have any of that. We don't have any of that. We consume a little bit of this. This is the reaction taking place, and some of this reacts to produce the same quantity of that and the same quantity of that. So in my E line, I have 0.1245 minus X, and I have an X here and an X here. Now, this is an equilibrium, so it has to have a K something. What is it, a Ka or a Kb? Well, what is this, an acid or a base? That's a base. So I need the Kb of A minus. The problem, they gave me the Ka of the conjugate acid. We'll worry about that in just a moment. Now we'll go ahead and write the expression. HA, this is the law of mass action, or what I call the equilibrium constant expression, okay, over A minus. So that's everything. Now, if I could plug it in, I might be able to finish this problem. To get Kb, all right, to get Kb, I'm going to take Kw divided by Ka, because Ka times Kb gives you Kw. So I'm going to plug those numbers in. Kw is 1.0 times 10 to the minus 14. Ka was there on the screen, 1.54 times 10 to the minus 5. Okay, so that's that portion of the problem. And I think I have a value for that already. It's a 6.494. Again, I'm carrying extra sig figs along for the ride for right now. 6.494 times 10 to the minus 10. That's the Kb of this base. Now that's going to be equal to the HA times the OH minus, so that's going to be X times X, or X squared, over 0.1245 minus X. Do you suppose that if we're solving this thing for X, we could assume that X is much, much smaller than this initial concentration of 0.1245? I think it's a good assumption because that's a tiny K value. It's a tiny K value, this equilibrium doesn't go very far to the right at all. So when I assume, okay, I can finish solving this problem. I'm going to move it over here a little way. So what you see here is going to be the 6.494 times 10 to the minus 10 times the denominator. I'm bringing it up over here on this side, 1245. That's going to equal X squared. So then what am I going to do? I'm going to take the square root of both sides. So the square root of this and the square root of that. That'll give me X. And the value for X is 8.99 times 10 to the minus 6. Now never stop this X solving without going back to your assumption. Is this much, much smaller than X? Yes, it is. Good assumption. I checked that out. Now, look at the problem. It wants to know pH, not X. pH, how do we get that from X? Well, let's figure out what X is. X is the OH minus concentration. So if I were to take the negative log of that, what would that give me? It would give me the POH. So POH is the negative log of this number, 8.99 times 10 to the minus 6. Now I've run out of room, haven't I? I'm going to go way over here to the left-hand side with the value of the pOH that gives me. pOH. The pOH that gives me is 5.046. Now, a lot of people will blindly take a negative log of that number and say, finally got it. But that wouldn't give it to you. That's still the pOH. So then the pH would be 14 minus that number. And finally, we will have the pH. The pH value is 8.954. 8.954. So we ask ourselves, does this number make sense? Okay? Remember, we are titrating a weak acid with a strong base. At the equivalence point, that will always have a pH greater than 7. And lo and behold, that is a pH greater than 7. But you can't know what the value is exactly until you go through and do this ICE work after you've done the one-way reaction. Now, what did I tell you? I told you that when you're at the equivalence point, it is quite an ordeal to determine the pH. This is a lot of calculations. You cannot just memorize it. The reactions need to make sense, okay? How you finish the problem needs to make sense to you. And if it doesn't make sense, please get help, whether it's from me or from somebody else. But you need to be able to understand why the reactions are written the way they are. Once it makes sense, we can make variations to it, and it won't throw you for a loop.